A huge thanks to my Patreon supporters for making this episode possible. Wow! Video! Welcome back, fellow mathematicians. Today I would like to cover something which made the rounds on Twitter, Facebook, basically everywhere on the internet. Like 2 weeks back or something of that sort. I'm a bit late on the topic because I have so much stuff to do at the moment and terribly sorry. But never mind, it's still a very interesting result. And I think the way to get there is pretty interesting, and I have seen a few videos on this topic already and a few explanatory posts over on Twitter and the like, but I thought I might as well make a video on it because it's on the one hand really interesting and I found some of the other explanations not too nice, so I would like to bring it to you guys in my style. And what is the whole thing about? Well, 2 high school students, they were females if I'm not mistaken, were able to prove the Pythagorean theorem, which is in and of itself nothing special, to be honest, because there's literally a book on proofs of Papa Pythagoras and there are hundreds of different proofs in there. I for myself came up with different proofs of Pythagoras over the course of my lifetime, bunch of those, and they only proved like one, so how is this special? Well, it's in that sense special that they were using sources claim that they were using trigonometry, but it's more a calculus approach to the whole thing. I wouldn't say that it's strictly trigonometry. Even trigonometry is just analytic geometry, which is just anal. So yeah, it's calculus. Let us just go with they proved it using calculus, and it's quite an interesting approach, to be honest. I really like it, and this is why I wanted to show it to you guys today. But before we get into the video, don't hesitate to leave some comments down below what you think about the results and what those 2 girls were able to put out there. They are high schoolers, so I don't think that there's much place for criticism here. You might not think that the proof is special in any kind of way. There are so many proofs for Pythagoras out there, but please consider they are 2 high schoolers. Something sparked their curiosity. They are trying to build their maths knowledge on their own. They are trying to prove things in high school already on their own, and then something like Pythagoras using calculus, infinite series, trigonometric identities, and so on, which is pretty outstanding if you ask me. If I asked one of my high school students, could you prove something for me? They don't even know what a proof is. So I think that this is quite outstanding in and of itself. And please don't be mean down there in the comments and say something shitty. It's just not nice. We should be really glad if our youth starts to engage in more curious things. Mathematics, physics, science in general, and especially female students, which is really cool. But do you know what also can spark your curiosity? The audiobooks and also podcasts and many other things in edutainment over on today's sponsor's website, Blinkist. If you are like me and you do not particularly enjoy reading books, or maybe you are just too busy at the moment to do so during your weekly routine, then Blinkist might be a great way to integrate your thirst for knowledge into your daily life again. The Blinkist app allows you to understand the most important things from over 5,500 non-fiction books and podcasts in just 15 minutes. With the help of Blinkist you can discover new perspectives, broaden your horizons, have exciting conversations and to experience mind-blowing aha moments. I listened to quite a bunch of Blinks already, and the one I enjoyed the most until now was The Man Who Solved the Market by Gregory Zuckerman. It's the story of a well-established mathematician, Jim Simons, and it features his life as a geometer all the way to him cracking Soviet codes. Maybe you have heard about him before. It's a really fun one and you should definitely check it out too. You can find the link to that down there in the description below. What's also really cool is that they just recently added Blinkist Connect to their list of features, which enables you to share one premium plan on 2 different accounts at no additional cost. That's a 2-for-1 deal that you don't want to miss out on. Trust me, you can share your most favorite books and podcasts and shortcasts and so on with your other beloved person that you are sharing your premium account with, and that is just great. You can shift around the books and the like, and you can tell each other what you like most. It's a 2-for-1 deal. It's just great. You shouldn't miss out on that. So why wait any longer? Get yourself 25% off Blinkist Premium and 2 memberships for the price of 1 today. Clicky on the linky down there. Just do it. Start your 7-day free trial today and get curious. And now we are going to dive into the main video. So this right here is a right triangle. Without loss of generality, vlog, we are going to assume that C is the hypotenuse, meaning since it's opposite of the 90-degree angle, which is the biggest angle in the triangle, it's also the biggest side. And we are going to say, without loss of generality, that it's greater than both B and A. And just for visualization purposes, we are going to say that A is also smaller than B, but it could quite possibly also be the same as B, obviously, if it's an isosceles right triangle. So this is the first thing that we should state here. Okay, next we are going to continue, and what we are going to do is, or what the students did, I should rather say, we are going to double this triangle. I was speaking of isosceles triangles just now. So what we are going to do is we are going to glue this triangle once again on this side here. We're going to end up with an isosceles triangle. That's the side length A once again, that's a side length C. Now, we also got some angles in this triangle. For example, we get, in the original right triangle, we are going to get alpha opposite of A. And we are going to get beta down here, and gamma is just a right angle. So we also get the same ones here. This up here is alpha, and this down here is beta. Now, we can play around with those expressions a tiny little bit. How about we are going to use the law of sines? This is where the first trigonometric identity comes in. Law of sines just tells us that the ratio of 2 sides in a triangle is equal to the sines of the angles in ratio. Meaning, how about we take a look at this side right here in the isosceles triangle, which is nothing other than 2a. So the ratio of 2a divided by the original hypotenuse C is equal to. Okay, now we are going to take a look at the other ones that we got right here. No, we are going to take a look at, oh yeah, C, that is totally right. I'm terribly sorry. Now, if we were to just consider this isosceles triangle, I was looking at the right triangle, but this is obviously wrong. We were constructing the isosceles one here. Then what is the ratio of the corresponding angles that we got? The angle opposite of 2a is 2 alpha. So this right here is corresponding to the sine of 2 alpha divided by, that's the ratio that I was talking about. The angle opposite of C in this isosceles triangle is beta. So divided by sine of beta. Now the cool thing is we started off with a right triangle, and in right triangles it's rather easy to formulate ourselves something for the sine, for example. If we take a look at the sine of beta here in the right triangle, then it's nothing other than the opposite B divided by our hypotenuse C. And we can plug this definition for sine of beta into here, meaning this is going to be the same as sine of 2 alpha divided by B divided by C. Or if we were to take the reciprocal here, we are going to end up with 2a divided by c is equal to c times the sine of 2 alpha divided by b. And now what we're going to do is we are going to multiply both sides by c. We are going to divide both sides by sine of 2 alpha divided by b. b is not equal to 0, so we can multiply both sides by it. And sine of 2 alpha is also not 0 because alpha is non-zero. And since it's in the interval from 0 to pi over 2, our triangle that we got right here, since alpha must be strictly less then our right angle, this is the proper explanation here, we can multiply everything safely, so that's not a problem. So we are going to bring c to this side, we are going to end up with c squared being equal to c squared, okay? You see, c squared, Papa Pythagoras, we got the first part done, this is pretty exciting, I know, right? 2ab divided by the sine of 2 alpha. Okay, that's the first part. But where do we want to go? We want to show that the hypotenuse squared is equal to the sum of the two cathets squared. So this is still missing. So we got this expression here, okay, nice, a and b are here, but we got sine of 2 alpha. That is not too nice. How can we deal with the sine of 2 alpha? Well, now we are going to take the calculus approach here. This is where calculus comes in. And what we are going to do is we are going to glue a little triangle right here in a right angle to this isosceles triangle. Then we are going to connect the lines here, and what we are going to do now is we are going to construct this triangle in such a way that the angle beta forms a right triangle with this angle that we have right here in this little corner. Now, what is this angle going to be right here in the corner? What's up with that construction? Well, this angle must be alpha. Why must it be alpha? Because in this right triangle, all interior angles add up to 180 degrees. Now, we got already a right angle here, meaning alpha and beta added together must also be 90 degrees for everything to add up to 180. Meaning, since beta is already here, we want this whole thing to be a right angle. This angle right here must be alpha. Okay, this is at least something that we know. Now, if this angle right here is alpha and this angle right here is 90 degrees, then obviously this angle down here must be beta by our former restriction. Don't forget, alpha plus beta is equal to 90 degrees. Okay, so this right triangle that we got right here now got a side length of 2a. It's obviously not equal to our original right triangle, but the cool thing is it's similar. It got the same interior angles, but it's scaled up by a certain ratio. Now we are going to continue this process a tiny little bit. We are going to elongate the side that we have right here. We are going to form another 90-degree angle right next to this beta. That's right here is a 90-degree angle. Now, by the similarity once again, you can go over everything. You are going to see that beta is right here. A straight line has 180 degrees in total as the angle. Beta, 90 degrees, well, this angle must be alpha once again, meaning this angle down here must be beta. And we are going to continue this process, and it's just going to continue on and on and on. What we are going to do is we are going to elongate this side of this triangle, right triangle. Now you might guess this right here is alpha and this right here is beta, and so on and so forth. This construction continues, well, up until infinity. And that's the beauty of this construction. What we are going to do is we are going to create ourselves an infinitely long triangle, you could say. It's not infinitely long, we are going to see, but at least it's an iteratively formed triangle with infinitely many little triangles attached to it. And do you know what the cool thing about this construction is, which I find to be the most intriguing part of the proof, is that this angle that we have right here, beta and alpha, forms a 90-degree angle. We have 2 alpha up here as the angle, and the angle down here really doesn't matter, since this right here is a right triangle now, a big old right triangle, and we can construct ourselves the sine of 2 alpha if we were just to find out the opposite side of 2 alpha, so what the length of this side is, and also what the length of the hypotenuse is. Meaning, if we were to draw out this triangle once again, this new one that we got, that's the infinitely iteratively constructed triangle that we are having. We are having the angle of 2 alpha up here, that's a 90-degree angle, and now we have those side lengths. We have the hypotenuse, I'm going to call it t, and we have this side length, meaning we can find out the sine of 2 alpha if we just get ourselves s divided by t. So this is our goal now. I hope you can understand. It's pretty easy to see, but it's also a pretty cool construction. This is why I think this proof is rather nice. Okay, so this side length right here, for example, the hypotenuse, is comprised of the original hypotenuse c. Okay, this is something that we know. But also this length right here, I'm going to call it t1. And this length, t2 and t3, and so on, up until infinity. The side length s that we have right here, the opposite is comprised of s1 and s2 and s3, and so on. And now we are going to calculate those one after another. And we are going to start off with s1. And we are going to make use of a nice fact which holds in every pair of similar triangles, namely that all the side lengths together are in ratio. For example, and this is why I choose B to be greater than A, such that we can see it a bit better. What about the ratio of the longer of the two cafetes, so B, and the hypotenuse? So in the original triangle for S1. For the original triangle, we're going to take a look at the ratio b divided by c. Could be 1/2. For example, b is just half as long as c. Then we are going to get the ratio 1/2, for example. Okay, now this triangle right here is similar. So let us take a look at the sketch. The longer of the two cafetes in here is 2a. So this means since it's similar, that's the part which is going to go up here in the ratio. And it's the same ratio as with S1. So those are going to evaluate to the same value. This is just one of the nice properties of similar triangles. And just like that, we get an expression for S1. Namely, if we were to solve for it, all of the lines have non-zero measure, so we can just solve for S1. S1 is equal to 2a divided by, so multiplying by c, 2ac divided by b. Okay, so we got ourselves S1. And now we can deal with T1. Oh, that kind of sucks. We don't have any of the two cafetes right here given. So we can't use the similarity at the moment. But that's not a problem. Let us find the longer of the two cafetes out once again. I'm going to give it a name. Let's call it D. Big old daddy's D. D for daddy. Oh, that is nice. Okay, let us take a look at the first triangle once again that we constructed. And let's put some things into ratio. So the ratio of D and 2a, for example, the two cafetes. D divided by 2a. It's the same as the ratio of the shorter of the two cafetes, so a divided by the longer one, b. Now we can solve for d, and we already have an expression. That's nice, that was easy. D is equal to 2a squared divided by b. And now we can deal with t1. So if we set t1 in ratio with the longer of the two cafetes, which is d, we are going to get, once again, the ratio of the hypotenuse, c divided by b. It's always the same procedure, setting the longer cafete in ratio with the hypotenuse, or the other way around. We can just take the reciprocal in case. Okay, and now we can solve for t1. So t1 is equal to d times c divided by b. But we know what d is. D is nothing other than 2a squared divided by b. So this is 2a squared c divided by b squared. Nice! We got a value for t1. And now we can continue this process. You can say this side length right here is e, for example. So if you want to find out s2, we are just going to calculate e at first. E in ratio with d, not a, is the same as, that's the shorter of the two, so a divided by b. We can multiply both sides by d, so e is equal to ad divided by b, but we know what d is. D is 2a squared divided by b, 2a to the third power divided by b squared. And maybe you can already see a pattern. The first thing that we found out in the ratio here, which was the longer of the two caveats, was 2a squared divided by b. And the next one, which is e, is 2a to the third power divided by b squared. Every time we find out a new one of those caveats, it's always going to raise the power of a and b by 1 consequently. And now we can plug this in once again. If we want to find out S2, we are going to get that S2 in ratio with E is the same as C divided by B, meaning consequently that S2 is equal to E times C divided by B. And now if we plug in E, we are going to get that this is 2a to the third power C divided by b to the third power. And maybe you can already spot a pattern here. What you're going to notice is that if we were to continue this process, S1 was 2ac divided by b. S2 is 2a cubed c divided by b cubed. Now you can guess what S3 is going to be. It's going to be 2a to the fifth power c divided by b to the fifth power. Same thing with t, but t has the property that we are going to go through all the even powers instead of the odd powers. So that is kind of curious. With this observation we can actually get ourselves an expression for the ith t or the ith s. If we take a look at the ith expression of s, then we started off with S1 here, so our index I starts at 1. 1, 2, and so on, up until infinity. We are always having the term 2c in here, which is going to be a constant term. But then, what we are going to get is, we are going to get a to the, well, all the odd powers. So 2i plus 1 divided by the same with b, 2i plus 1. We can actually rewrite this a tiny little bit because we can just use the exponentiation rules and turn this into a to the 2i times a. Same thing with the b down here, so we always get this constant term. So 2ac divided by b. We are going to be left with a to the 2i divided by b to the 2i, but by exponentiation rules we can bring the to the ith power to the outside basically. So this is a squared divided by b squared, but to the ith power. And now we can do the same construction for all the ti's. The ti's are going to be of the form, well, 2c is once again a constant factor, which is going to be in here. But this time we are going to go through all of our even terms. But our index this time starts at no, it starts at 1 once again. This really doesn't stop us. Yeah, starts at 1. So 2c, and then we are going to get a to the 2i divided by b to the 2i. And once again, by the same logic, we can bring the I to the outside, giving us 2c times a squared divided by b squared to the ith power. And don't forget what our t and s are. They are just the infinite sums, respectively, of all those si's and ti's added together. But for the t's, don't forget, we are also going to get this term of c up here. So our t is nothing other than c plus the sum over all of our ti's. And for s, we are going to have that this is just the sum over all of our si's, where I is greater or equal to 1. No, for the si's actually, I'm noticing this just now, since we start at 1, our I must start from 0 actually. There was probably a correction inside of the video already. Meaning for our t's, we are going to start our index at 1. I'm terribly sorry. No, what am I doing? 1, 1 and then 1 to 0. I'm so fucked in the head, seriously. Okay, so this right here starts at 0. And now we can start calculating those infinite series. And then we are basically done with the whole proof. Let us start off with the expression for t. So, or the expression for s, that's probably a bit easier. I don't give a shit, we started with t here, so we're going to continue with t here. Now, for the t part, we're going to get that t is c plus the infinite sum over what we got here, but we already did a bit of work here. So we get 2c to the front, and the next thing we are going to get is the sum where I is greater or equal to 1 of a squared divided by b squared to the I-th power. And this right here is just a geometric series. It's pretty easy to calculate, but the index starts at 1. We wanted to start at 0 in the normal case, so we are just going to add a 1 and subtract a 1 in here, and this way we are going to get rid of this problem. So this part right here is just included. This is going to give us the regular geometric series. So 1 divided by 1 minus a squared b squared, or if we were to expand this fraction by b squared over b squared, we are going to get that this is b squared divided by b squared minus a squared. And all of this minus 1. Minus 1, we are going to expand this fraction. It's going to be just b squared minus a squared over b squared minus a squared. We can distribute the negative sign into here, getting rid of the b squared if we were to add those together, meaning t is nothing other than c plus 2c times. And now b squared is going to be cancelled out. We are going to have a squared at the very top divided by b squared minus a squared. Okay, and now we can continue here. So if you want to bring those together, we are going to, I don't know, there are different ways to do so. We could factor out the c, for example. If we were to factor out the c, then we are going to get 1 plus, and the 2 was still here, 2a squared. And now what we are going to do is we expand the 1 that we got right here by b squared minus a squared. So we are going to get b squared minus a squared up here plus 2a squared. And this is going to get rid of the 2 right here on the a squared, giving us just b squared plus a squared with the factor of c. So c times b squared plus a squared divided by b squared minus a squared. So this right here is the term for t. So that was easy. How about the term for s? So s is our infinite summation of what we got right here, but we got the 2ac divided by b, which we could bring to the outside. And now we have the infinite series starting at 0, so that's a bit easier than this case, of a squared divided by b squared to the I-th power. We know what that is, we discussed this just now. This is just 2ac divided by b, and then we are going to get this term right here, but if we were to expand it by b squared over b squared, we are going to get b squared divided by b squared minus a squared. B and the squared is going to cancel out, giving us consequently 2abc divided by b squared minus a squared. And don't forget what we originally found out, namely that sine of 2 alpha is equal to s divided by t. But what is s divided by t? S divided by t is just the ratio of those two. So if we were to plug this in, we are going to get on the numerator 2abc divided by b squared minus a squared. And all of this divided by the other chunk that we got right here. C times b squared minus a plus a squared divided by b squared minus a squared. You're going to notice that the denominators are going to cancel out. Also, we get a c right here, giving us overall that the sine of 2 alpha is nothing other than 2ab divided by b squared plus a squared. Now, that might seem a bit familiar to you. If we take a look at the first thing that we got right here, in this expression we get 2ab divided by sine of 2 alpha. We can actually get this expression right here, which is nothing other than c squared. What we can do is we can divide both sides by sine of 2 alpha. We can do this, I explained it to you before. Multiply both sides by b squared plus a squared. Meaning b squared plus a squared is the same as 2ab divided by the sine of 2 alpha. But this right here is exactly c squared. And I shit you not, my boys, b squared plus a squared is equal to c squared, which is nothing other than Papa Pythagoras. And we can call this a big QE fucking D. And I thank you guys for watching, and I hope you enjoyed what you have seen today. I hope this explanation was okay to you. And I noticed that I'm casting a bit of a shadow today onto the board, and I'm terribly sorry about this. I was trying to play around with the lighting a bit more, but it doesn't seem to be working out as I wanted. But never mind, it is what it is right now. And I seriously hope you did enjoy what you have seen today. I certainly really like this proof, and it's a cool one. It's just very creative, and those two grills did a really fucking good job figuring this one out. I really liked it. It's pretty damn cool. And I hope you liked it too. Also, my camera stopped working right in the middle of the video. This video is a bit cursed, to be honest. But yeah, it is what it is. Also, don't forget to check out Blinkist. Sponsors keep the channel alive, so check it out. Just do the trial, okay? Just try it out. See if it's something for you. And if it's something for you, seriously make clicky on the linky. And that concludes it for today. Please stay safe, my boys. And up until the next video, I wish you guys a flammable day. See ya.